Welcome, fellow chemists, to the first video in the series on instrumental analysis. Today we will begin our journey with mass spectrometry. If hearing something like mass spectrometry scares you, let me start out with a calming disclaimer. It's usually shortened to mass spec or MS, so that makes things much easier, of course. Now for the real disclaimer, the goal of this series is to learn how to use various techniques to identify substances. It would hardly surprise you that there's plenty of mathematics and physics working behind the scenes. However, I will only mention whatever bits and pieces are absolutely necessary for us to be successful. Understanding these techniques is going to take a while, so without any further ado, let's get started. Mass spectrometry works by ionizing or removing an electron from a molecule. Hexane here would lose any one of its electrons, and what is left is considered a molecular ion. It's also a radical cation because it has an unpaired electron somewhere and is positively charged. However, the loss of that electron reduces the stability of the molecule, and it may break apart. If this bond breaks, we get these fragments. One of them would be a cation, and the other a radical, but we don't need to focus our attention there. Of course, other bonds could break, and we could get these fragments too. The spectrum, or readout, displays the relative abundance of the fragments on the y-axis. The more often a fragment hits the detector, the higher the peak goes up. The most common peak will be assigned a value of 100 and all others relative to it. The mass of the fragment can be found on the x-axis with the label mz, or mass to charge ratio. The maximum value here depends on the mass of the molecular ion itself. Since the peaks grow from the bottom up, I need to move the tick marks below the axis. Now to make this a realish spectrum, let me plot some modified data. The higher the peak, the more abundant the fragment is, but you probably should not look at the height of the peaks first. The MZ ratio on the bottom is telling us the mass of the fragment, and this tall one over here on the right is possibly the most important. Its value is 86, and since it's the highest mass, it must be the peak for the molecular ion. It may be very likely that the molecular ion will fragment, but very likely does not mean always will. This narrows down the possible identities of the molecule, but without any context it can be very difficult without resorting to finding a matching spectrum. So if I tell you it is an alkane, can you figure out the formula? Okay, so you've figured out the formula is C6H14, and that means it is one of the following. It is still too early for us to identify which of the five it is, but if you figured out the formula of the molecule, I'm sure you can figure out the formulas of the fragments. The fragment at NZ71 is 15 mass units smaller, which means it has 1 fewer carbon and 3 fewer hydrogens. As we work our way through the remaining peaks, we get C4H9, C3H7, C2H5, and finally CH3. Even though we know there are only 5 possibilities for the substance, identifying the fragments hasn't really got us any closer to an answer. For that, we need to say goodbye to the spectrum for a bit. And we need to say hello to our friends the carbocations, because that is what the mass spec detects. If you watch any of the other organic reaction videos, you'll know two things about them. First, they are called methyl, primary, secondary, and tertiary. Also, stability increases from methyl up to tertiary. The more stable the carbocation, the more likely it is to form, actually reach the detector, and be measured. The screen is going to get quite crowded soon, and these colors will be used to identify the fragments as one of these types. Let's take a look at what happens to the potential molecules as they start to fragment, beginning with hexane since we've already seen it. We get a methyl primary pair, or two different primary pairs. For the remaining four, I will only show a possible, if not the only most stable fragment pair. It would be beneficial for you to try and identify other potential pairs on your own. 2-methyl and 3-methylpentane both create secondary primary fragments. 2,2-dimethylbutane makes a tertiary primary pair, and 2,3-dimethylbutane makes two secondary fragments. If these fragments are produced, they would show up on the spectra, which means a bit of logic allows us to remove two of these candidates. Knowing the masses of the fragments is quite helpful. Remember that the largest peak and therefore most likely fragment produced was at mass 57. The most stable fragments of 2,3-dimethylbutane and 2-methylpentane have masses of 43, which means on their spectra we would expect the largest peak to be at 43, so we can eliminate these from contention. We can also narrow it down further if we take a closer look at 2,2-dimethylbutane. If we randomly break one of the 5 bonds on this molecule, 80% of the time we will get fragments of masses 71 and 15. Since those peaks were not very big, it seems unlikely that this molecule is one of the candidates. Now, techniques like this are often used in conjunction with others, so the fact we have narrowed it down to just 2 candidates is about as good as we can do without any additional analysis. But if I know you, you really want to figure out what molecule made this spectrum, so let's add the other candidates modified in the same manner. Given how similar they are, we really did a good job in narrowing down the options because we were looking at essentially the same thing. But essentially the same is not the same, so which molecule made which spectrum? This is where the heights of the peaks are really useful. In the original, we see that a fragment of mass 43 is more common than that of 29. However, in the other, the fragment of mass 29 is more common than 43. This means the one on the bottom is caused by a molecule that is more likely to produce a fragment of mass 29. Hexane does produce primary fragments of mass 29, but in one scenario it actually produces two primary fragments of mass 43. Meanwhile, the most likely stable fragments of 3-methylpentane include mass 29, but not 43. By this logic, it is sensible to assign the spectrum on the bottom to 3-methylpentane, which means we can finally conclude that the original was produced by hexane. We have just scratched the surface of mass spec, and there is a way to go before the point where I can just put some spectra on the screen and you can identify the molecule, so be patient. Of course, I may have to, kind of explain what on earth this tiny spike near MZ87 actually is, and I'll do that next video. Before that though, I'm going to leave you with two spectra of alkanes with the same molecular formula. Good luck, and as always, thank you very much for watching.